All right, so question one of this uh, paper is about unit conversion. So question one is saying, but A convert 95 kilometers per hour to meters per second. Convert 95 kilometers per hour to meters per second. But B is saying convert 5.0 times 10 to the power 3 square millimeters to square meters. All right, so we discussed this particular component. I'm sure this was the first topic that we discussed, you and I. So when it comes to unit conversions, I mentioned to say these are some of the questions or simplest questions that you are going to ever find in your assessment, whether be it an exam, be it a test, be it a quiz. As long as you found a question on unit conversion, that should be a free mark on your end. That's the strategy that you're supposed to make. Because when it comes to unit conversion, the only thing that you're supposed to make sure you get correct is what we call the conversion factor, which by now you know the definition of a conversion factor. Say it's a ratio between two distinct units of measurement that is going to give us one when you're comparing them to each other, which means whatever you have of this other one should give you one of the other one. Even this particular side, whatever you have of that particular one should be equal to one of the other unit of measurement. So in this particular case, we'll start with A, where they've told us to convert 95 kilometers per hour into meters per second like this. So the first thing you're supposed to notice is that we are converting kilometers into meters and we are converting hours into seconds like that, of which if you um get your conversion factors right, you should be able to notice to say a kilometer is made up of what? Is made up of 1,000 meters, which means 1 kilometer is equal to what? Is equal to 10 to the power 3 meters, which is 1,000 meters. Or still, when it comes to seconds, um, uh, 1 hour is made up of 60 minutes. 1 minute is made up of 60 seconds. So which means we are multiplying 60 by 60, and that basically means 1 hour is equal to 3,600 seconds like that. So this is, or these are the two conversion factors, the ratios that you are going to use that are giving us one of the other guy being equated to whatever magnitude you have in the other unit of measurement. So this is the same as 95 kilometers over 1 hour. So remember I said the first thing we'll do is multiply by your conversion factor. Whichever one you start with, that won't change the answer. Just make sure to say whatever is a denominator here should be a numerator there so that it's able to cancel out. Whatever is a numerator here should be a denominator on the conversion factor so that all these should be able to do what? Should be able to cancel out. So when it comes to hours, we know to say we have 1 hour here, which is being equal to what? Which is being equal to 3,600 seconds or 3,600 seconds. Whilst when it comes to the kilometer here will now be a denominator multiplied by the number of meters, which is 10 to the power 3 meters. So the kilometer is going to cancel out with that kilometer, or still that hour is living together with that hour. So what are we remaining with? We're remaining with 95 multiplied by 10 to the power 3 meters, which is the same as 95 multiplied by 1,000, which is going to give us approximately 95,000 95,000 meters divided by 3,600 seconds. And this should be able to give us our final answer. So what is going to be the final answer? What's going to be the final answer? Okay, so I'm getting 26.39 meters per second. So this is it, our conversion in this particular case. As simple as that. That is part A. Part B is also about conversion. It's also dealing with, or this one is dealing with area. So we have 5.0 times 10 to the power 3 square millimeters. We are converting this into square meters, like that. Okay, so we're still dealing with area in this particular case. The only thing that is different here is that our unit of measurement is having what? Is having a certain power to signify that we're dealing with the area, or to show us that we're dealing with the area. So we're having this square here. And I explained this in the first class. I emphasized to say when you're dealing with such conversions, it's as simple as doing these regular conversions that we've done here. The only thing that you're going to do different is that you're supposed to introduce that same power that is uh, being used as a point of reference to your conversion factor, which means, for example, in this particular case, the conversion factor that I had, for example, this guy here, if I wanted to convert into square meters, what was I going to do? I was just going to introduce a square to my conversion factor. As simple as that. It doesn't change a lot, or it doesn't complicate anything in this particular case. So I have 5.0 times 10 to the power 3 square millimeters, like that. What am I going to do? I'm going to multiply this by the conversion factor. And my conversion factor will be a conversion factor from millimeters into meters. So we know to say 10 millimeters make up 1 centimeter. 100 centimeters make up 1 meter. So how many millimeters make up 1 meter? Milli. From the table of prefixes, those who remember how much is a milli? It's 10 to the power what?
It's 10 to the power of -3.
Okay, so it was going to be power -3 if the meter was the one that had a power. In this particular case, it's going to be 10 to the power 3 millimeters, since the millimeters are the ones that are supposed to be a lot to make up this 1 meter that we have here. If it was the other way around, we are going to say 1 millimeter is equal to 10 to the power -3 meters. Like this. This is the difference that exists depending on which one you've used to reference one. If the one that is smaller is the one that you've represented with one here, that means this guy is supposed to have a negative power. If the one that is bigger is the one that is carrying a one, or that is being represented with a one, that means the smaller guy here is supposed to carry a positive power. So this is what we're going to do. We have a millimeter as a numerator in this particular case, so it's supposed to be a denominator on my conversion factor. So I'm going to say 10 to the power 3 millimeters. That just basically gives me 1 meter. I'll put this in brackets. Then I'm going to square it like that. That means my brackets my square here is supposed to distribute. Remember, this is grade 12 mathematics. If I distribute a square inside the brackets here, that means it's going to apply to both the numerator and the denominator. So I'm going to have 1 squared, m squared. Even here, I have this 10 to the power 3 in to my mini brackets there with a square outside, then even the millimeter there squared. Everything is supposed to be squared, starting from the numbers, the values themselves that are indicating magnitude to the units of measurement. Everything is going to carry this same power. So 1 squared is just basically 1. So in short, I'm ending up with 5.0 times 10 to the power 3 square millimeters being multiplied to, I have 1 squared here. This is just basically 1. So which means on my numerator, I'm going to have 1 multiplied by, I'm remaining with the meter squared. Then what about my denominator? I have 10, I have 3 here and 2. What's happening to the 3 and 2? The powers? How are we going to manipulate the powers?
You multiply them.
You multiply the powers. So we're going to have 10 to the power what? 10 to the power 6. and the square millimeters. Now we can see to say we have square millimeters there and square millimeters there, which means these two guys can now cancel out because they are irrelevant in our conversion. We are looking for the square meter in this particular case. And you can proceed to perform your mathematics here. So we're going to say 5 by 10 to the power 3 multiplied by 1 square meter divided by 10 to the power 6. What final answer are we getting? Those with calculators? Those with calculators?
I'm getting 5 times 10 to the power of negative 3.
Okay, so we have 5.0 times 10 to the power minus 3 square meters, of which this is justified because we said if you are converting into a bigger value from a smaller value, here it had a positive value or it had a positive exponent showing that it is a smaller value, of which we've just converted it into a much bigger unit of measurement. So it's supposed to give us a much smaller value. Hence, we are getting a negative exponent in this particular case, and it justifies our answer. So, as simple as that, you will have calculated perfectly your conversions for both part A and part B, just like that. So that was question 1. We can move on to the next question. Question 2 is saying a proposed equation for the period t of a simple pendulum is t, which is period, being equal to k the square root of open bracket m over gl, close your bracket, where m is mass, g is acceleration due to gravity, l is the length, and the k is a constant. A. Determine the dimensions of the right-hand side of the equation. Determine the dimensions of the right-hand side of the equation. B. State whether the equation is dimensionally correct. State whether the equation is dimensionally correct. And this is from tutorial sheet 2. This question is from tutorial sheet 2 because in tutorial sheet 2, that's where we solved dimension analysis. And I emphasized the importance of that particular topic because whether you like it or not, be it your quiz, be it your test, be it your exam, dimension analysis is going to be there. So it's either you know it or you're willing to donate some marks. You're willing to lose some marks for free. And these are very simple questions because we explained to say when we talk about a dimension, we're just basically describing the measurable characteristic of any physical quantity. So for example, you are going to have mass. Mass is a measurable characteristic. So mass is going to have what? Mass is going to have its own dimension. If you are talking about distance, distance is a measure of what? Distance is a measure of length. That means the measurable characteristic, the dimension of distance is what? Is the length. If you're talking about acceleration, you know to say acceleration is measuring what? Is measuring the rate of change of velocity, which means we're talking about distance over what? Over time squared, which means the dimensions of your acceleration are just basically length and the time squared. So that is what we talked about last time. Now, they are saying we should determine the dimensions of the right-hand side of our equation. Can we surely fail to do that? No, because they've already given us what is on the right-hand side. The only thing we're supposed to do is find the overall dimensions. Plug in the dimensions for each of these guys that we have here, then simplify your equation so that you come up with your overall dimension. And if you remember, we talked about this to say when it comes to dimension analysis, one of its limitations is that it doesn't deal with values that are dimensionless. We can talk about cosines. We can talk about whole numbers. For example, one. One doesn't have a dimension. It doesn't have a measurable characteristic. So we ignore those guys when performing dimension analysis. Then here, part B, they're saying state whether the equation is dimensionally correct. And we say in order for an equation to be dimensionally correct, it is supposed to be dimensionally consistent, which means the dimensions on your left-hand side of your equation should be equal to the dimensions on your right-hand side of your equation. That is it? That is what we explain. So first things first, we start with our part A. Period T, the equation we've been given is that period T is equal to, we have K. Then we have open brackets. We have mass over gravity multiplied by length. This is what we've been given here. This is the equation that we have. Now, in part A, they're saying we're supposed to determine the dimensions on the right-hand side of your equation. So anyone who has an idea, how are we going about this guy? Remember we said we have what? We have mass. The dimensions of mass are what? It's mass itself, because it's a measurable characteristic. We have length in this particular case. The measurable characteristic of length is what? Is length itself. It's its own dimension. Then, when given acceleration, and we've said the acceleration is what is the rate of change of velocity, which means it's distance, of which distance has a dimension of length divided by time squared. Hence, that's why we just say the dimensions of acceleration are LT to the power minus 2, which means the time is having um, a power there of minus 2 to explain that it is a denominator with a square power in this particular case. So that is what we have. Whilst they've told us to say k is a constant, and if it's a constant, we know to say it's a dimensionless. So we're going to ignore it in this particular case. Dimensionless. I hope I've written the correct English. Dimensionless. Yeah, this is physics. We don't care about English anyway. So what do we have on the right hand side? We have this value of k, or this guy, which is k, and we said we can basically ignore this guy from our equation since it's not necessary. That means we're supposed to deal with these three guys that are under the square root sign. So what are going to be the dimensions there, or how we're going to manipulate our equation? This is under a square root. When something is under a square root and you want not to show the square root, what power does it attain? What power does it attain? When something is under a square root, it's the same as what? Let's say if I have the square root of t here. Under a square root, is it necessarily a 2 memory? If I want to write this t, I don't want to change the expression of this. This is the same as t to the power half. So it's half. So which means this is the same as I have everything in the brackets, which is mass over gravity multiplied by length to the power what? To the power half. This is what I have in this particular case. So we can start by first manipulating what is in the brackets. Then when we find our final dimensions, we apply the power half to see what we're going to have. So under the brackets, I have mass over gravity multiplied by length. So this is going to be equal to, I have mass as my denominator. I'm now plugging in my dimensions here over, I have gravity, which I've said this is LT to the power minus 2 here. And this is being multiplied by what? By length. Those who remember, I said when you're showing dimensions, what are we supposed to do? We're showing dimensions of the right-hand side, which means on your left-hand side, I haven't indicated the equal sign. You're supposed to put your value in square brackets to show them that what you are solving for is to find the dimensions. So in this particular case, you just say the dimensions of M over GL like this will be equal to, then you put this on your right-hand side. That is what we do. Don't forget the square brackets here because they might mark you wrong. All right, so we're going to have M divided by, we have LT to the power minus 2 multiplied by L. What is this going to give us? Going to give us L squared T to the power minus 2 like this. This is what we are having. If we proceed now, we can see to say we cannot simplify this equation further. You cannot simplify it any further because we have mass, we have length, and time. You cannot multiply these, you cannot divide these guys. So we can just apply the half that I've mentioned. So we'll say our dimensions of GL like that will be equal to, I can put this into my brackets. I have m over, I have L squared and t to the power minus 2 like that, squared to the power half like this. Okay, what is this half going to do to our equation? It's going to be, what did we say in part 1? We said if we have a power here outside the brackets, how do we distribute it inside? It's going to be distributed to everything that is inside, which means the mass is going to have power half, the length is going to be multiplied to power half, and even the time itself is going to be multiplied to power half like that. Hence, we're going to get our dimensions being equal to, I have my m to the power half, m to the power half, since I can't simplify that any further. Then I have 2 multiplied by half. 2 multiplied by half here. This is just going to give me 1, which means length is going to remain with it, the power 1. Then half multiplied by negative 2, this is also going to give me negative 1, which means the time is only going to have what? It's going to have the power of negative 1 like this, which means that is basically what I am having. So these are the overall dimensions of this particular equation. If you leave your answer here, they are going to give you all the marks minus nothing, minus nothing. But if you want to leave it into this form, how is it going to exist? Anyone with an idea? How is it going to exist? Of course, we're going to have mass to the power half. And what about length? Length is a denominator, so if it has a power of 1. So if we take it at the top there, it's going to change its power to the power of negative 1. Then what will happen to t, which is initially having a power of negative 1 already? What power are we going to have? What power are we going to have for t? Guys, to be positive. It's negative. We take it at the top here. It's going to change the sign of the power. So these are our final dimensions of this particular expression. As simple as that. Part B is saying state whether the equation is dimensionally correct. State whether the equation is dimensionally correct. So how do you check if the equation is dimensionally correct? You check if the dimensions on your left-hand side are equal to the dimensions on your right-hand side. So if you look at the left-hand side, they've told us to say this is the period, of which period is just what? Period is the time taken for one complete oscillation. This is a pendulum. We know what the definition of period is. It's the time taken. So period is going to do what? Period T is going to have the dimensions of what? Is going to have the dimensions of time, like that. So this is our left-hand side. Then if you look at our right-hand side, which is this guy that we've calculated, you're going to notice to say these are the dimensions that we're having. That is the dimensions that we're having there. So if you compare the left-hand side and the right-hand side here, you can tell to say these sides are not equal. Left-hand side, or dimensions on the left-hand side, are not equal to the dimensions on the right-hand side. Hence, the equation is not dimensionally dimensionally correct. Just like that. That means you're done with this particular question. So just check the dimensions on your left and dimensions on your right. Are they similar? If yes, the equation is dimensionally correct. If not, the equation is dimensionally inconsistent. Yes, Nyawali?
Um, I'm a bit lost, I think, on the here where we had this equation mass over g multiplied by length. There
Yeah.
was a power there. I think I got lost on how we expanded on that one.
Which power? The half here?
The half, yes, there.
Oh, yes. So I said this half, first we'll reserve it. First, let's simplify what is inside the brackets. So we simplified what is inside the brackets from here up to here, because this was the simplest form. Then we reintroduced the power here. So we brought back the power, then we distributed it on both the numerator and the denominator. So I said if we distribute it to the mass, it's going to be mass to the power half. Whilst after simplifying, we notice to say the length here. Let's use this one. The length here has a power of what? Has a power of 2. So if we multiply this half by this 2, we're going to end up with what? We're going to end up with 1. So 2 multiplied by half, that is 1. Hence, here we're only having length to the power 1, or L to the power 1. Even here, the time is having a power of negative 2. If you multiply half here multiplied by negative 2, you're only going to get negative 1. And that is where this equation is coming from. I hope that
All
answers
right,
the
thank you.
question.
Yes, it does.
All right, all right. Any other question? Any other question? All right. If not, let's look at question 3. And question 3 is saying three forces act at a point. So we have three forces that are acting at a point. A, determine the resultant horizontal component of the forces. Determine the resultant horizontal component of the forces. B, determine the resultant vertical component of the forces. And C, calculate the magnitude of the resultant force. Calculate the magnitude of the resultant force. So this is about vectors. This is the question about vectors. I sent you the video on the tutorial sheet 3, which is on vectors. It's already solved, so I hope you've gone through that one, even though it's not part of your quiz necessarily, but you can still do the learning because it's a very simple topic when it also comes to vectors. So there are three forces in this particular case that are acting at a point. And the first thing is they want us to determine the resultant component in the x-axis. The resultant component in the y-axis, then calculate the magnitude of the resultant force. So if all these three forces are acting at a point, what are we going to notice? You're going to notice to say this is the same as I have my x or y plane. Let me do this. Let me draw a very simple x or y plane. 270. And let's say this is my x-axis at 0, 0. Yeah, like this. You're going to notice that this is my x and this is my y. So if they've told me to say there is a point, there is a point, I'm going to put this point here. Let's use it as a point of reference. I'm going to put this particular point here on the middle so that we see our vectors clearly. So they've told us to say the first vector, I'll put the vectors in red. They've told us to say the first vector is due east, which means it's pointing along the x-axis. So my first vector here is due east, 8 newtons due east, and it's the biggest, so we have to show to say it's big. Okay, That is my first vector. Then my second vector is due north, which is F2. Due north is 6 newtons. So it has to be smaller than the first one. We'll say like this. Oh, it's reaching at the top. All right. Then my first vector is due west, which means it's pointing in that particular direction, and it should be smaller than the other two. So these are the three vectors that I'm having. These are the three vectors. Yeah. So this is 8 newtons. This is 6 newtons. And this is what? This is 5 newtons. So there's no need in order for you to start struggling with finding the angles and everything here, because the angles that or the directions of the vectors that have been used are direct angles. For example, here along the x, we not say this is 0 or 360 degrees. Then here we not say from the positive x-axis, this is 90 degrees. Then here from the positive y-axis, from the positive x-axis, we know to say this is 100 and what? 180 degrees. From there up to there, that is a straight angle. So you're not supposed to panic or start struggling finding or calculating the directions of your vectors. Here, it's not necessary. So the only thing you're supposed to do is find the components of each vector in their x and y components, then add for those in the x, and add also for those in the y. Then after that, use the Pythagoras theorem, where your magnitude of your vector will be equal to Rx squared plus Ry squared. This is what we use always. So the first things first that we can do is first find the resultants of each of these. So F1, F1, since I'm using or since I'm resolving these vectors with reference to the positive x-axis, this one, that means always, in this particular case, my x-axis or my x component is going to carry a cos, whilst my y component should do what? Should carry a sine. This is what we do when we're following the directions strictly using the positive x-axis. So for F1, which is 8, we know to say this is 0. So we're going to say the x component here, the y component. Let me not say F1 only here at the top. Let's generalize it so that we plug in for everything. Let's just say we have a mini table here for x components and y components. Then here, that's why we're going to have our values. So, where is this? I'll have my F1, then I have my F2, then I have my F3. So for F1, the x component is going to carry a cosine. So I'm going to say 8 cos 0. What will be the value of 8 cos 0? Of course, cos 0 is just equal to 1, which means 8 cos 0 is still going to give us what? It's still going to give us 8. Or still, if we say 8 sine 0 is what? Or the x component, or the y component, I mean. Initially, when you reach that pro level of solving vectors, if you just see that this is on the x-axis, you should be able to automatically tell that the y component is going to be equal to 0. But since maybe some of you are still trying to figure out the way to manipulate vectors, you can still do 8 sine 0. You're going to notice to say sine 0 is just basically 0. Hence, 8 multiplied by sine 0, the y component of F1 is going to be equal to 0. The same thing is going to apply to the 6 Newton force here that we have. This one is also due north, which means it's only existing in the y component, which means the x component will be equal to 0, because we said the angle here is 90. So we're going to say 6 cos 90, cos 90 is 0. So this is going to give us what? This is going to give us a 0. Then 6 sin 90 is 1. So this is going to give us a 6 here. Then we have this one. This one is due north. I mean, it's due west, so which means the angle that we're using is 180. So we're going to say 5 cos 180. Cos 180 is -1, which means the x component will be -1 multiplied by 5. This is going to give us -1, whilst, I mean -5 rather, not -1. It is going to give us -5, whilst the the y component will be 0 because 1a cos 1a sine 180 is 0. So this is also going to be equal to 0. So to answer question A now, question A is saying determine the resultant horizontal component. So horizontal resultant, I'm just adding these that are in the x-axis. So 8 plus negative 5, this is going to give me 3 newtons. So Rx will be equal to what? Will be equal to 3 newtons. Whilst B is saying I should find the resultant in the y. So Ry will be equal to 0 plus 6 plus 0. This is going to give me 60 newtons like this. C is saying I should calculate the resultant, and hence my resultant, which is the magnitude of R, will be equal to, I'll open my brackets like that. I have Rx, which is 3 newtons squared, plus Ry, which will be 6 newtons squared. All right. So my resultant of R will be equal to, anyone who has already found the final answer, this is going to give me 9 plus 36. This will give me, what is it going to give me? 45. Then you get your square root of 45. And the square root of 45 will be 6.71 newtons. 6.71 newtons as the resultant. Just like that, you are done. Just like that, you are done with this particular question.